All right, welcome back to the study hall for March 3rd. We just did the whole rules thing. Division inequalities today in Quant. And here's the copyright notice screen again. They're either from the free GMAT prep software or from our materials. And let's do one. This one is from us. Give it a shot. And make sure, don't forget where the multiple choice answers are. Those are located here, underneath your name. Okay, go for it. Okay, we should be wrapping this up here. Remember, this is a test where you can't not answer things on this test. So there's the point where you definitely need to guess, even if you're not sure how this is going to work out. Data switching is a problem. So if you are Annie or Ashley or Ashton or Dave, Ryan, Pranav, Test 1, Teamy, let's go ahead and pick an answer to this thing. I mean, the answers are located here in the area underneath your name where there's that letter A there. Okay, so a couple of you still haven't picked answers yet, but we gotta move with it. All right, so the data consistency problem, all right? So, and again, this is what do the answers to a question like that look like? Like, is this thing less than that thing, question mark? Actually, yeah, I can see yours. What kind of question is this? So yes or no question, right? So if you think about the procedure for these kinds of things, you know how it works, right? You try to prove not sufficient with these yes/no questions. So remember, there's two possibilities, which are you always want to try. We've had whole study hall sessions on this specific thing too, but remember that you need to translate the whole ideas of yes and no into symbols and numbers and stuff like that. You don't want to leave this in the form of yes and no. So the yes case is that this is less than that. The no case is that this is not less than that, which means it's greater than or equal to, right? So the goal here basically is to see if we can get both of those to happen, then that's not sufficient. And if he can't, then that's sufficient. So there we go. Okay. So what's the deal? I mean, what you're going to find with inequalities in general is that in a lot of these cases, you're going to have to start thinking about cases of numbers. Like if you, with data sufficiency in general across the board, there's going to be basically two different families of approaches to these problems. See, with inequalities, though, there's a lot of things getting in the way of doing algebra with an inequality. I mean, one thing getting in the way of that is signs, because there's this whole notion of flipping inequalities around with certain operations and stuff. And then there's also, what if extremes and things like that. Getting things to turn into this is a little bit weird with algebra. So if you have inequalities with data sufficiency, the point is that you should be ready to do this. Maybe not every single time. I mean, you'll occasionally get some inequalities that you can actually just solve algebraically, but for the most part, you should be ready to do this with inequalities. So, all right, let's talk about this. What's the deal with this statement? I mean, well, with this kind of problem, you might want to actually deal with statement 2 first, just because it is simpler looking. It's like an easier point of entry. So it's not as hard to come up with cases for number 2, or the meaning of number 2 at least doesn't have to be discerned or decoded. Or like number 2 says exactly what it looks like it says. It says A is more than B. So let's test some cases. I mean, we need to make sure that these are true. So yeah, we can use 2 and 1. So let's do that. And again, because you can do statements in either order, it makes sense to just knock out statement 2 first, right? So let's test cases for statement 2. Let's use 2 and 1, sure, right? So A, B, and then what we should do is make a table. Like whenever you test cases, it's always a good idea to make columns that correspond to the different things that you're actually going to be using. So like here we have that expression, and we have that expression. Just resize them so they'll fit in the table. All right. So there we go. Yes. Okay, let's use 2 and 1. And I mean, when you do this, like making the table should come pretty naturally, because you should just like think about what do I have to do with these numbers once I pick them, and then whatever it is that you do with the numbers, just put it into a table. I mean, like even if you can test a case or 2 in your head, it's still good practice to just do it. Just put it in the table form so you get used to the habit. So okay, if A is 2 and B is 1, then this is 1/3. And this is 1/2 plus 1. So that's definitely more. The right-hand side is definitely more. Okay. What are we trying to do now? Like, what is our only goal in life at this point, so to speak? Once you've got this to happen, what are we trying to do? Yeah, be careful to prove it wrong. I mean, I think you're probably thinking of the right idea there, but there's no such thing as right and wrong with data sufficiency. I mean, we got this to be less than that. Yeah, we want to make this greater than or equal to that. Again, but make sure that you're not thinking of these in terms of abstractions. Like, make sure you're not thinking of, I need to get a no or prove it wrong. I mean, because those are not things. I mean, if you're typing that because you're being too lazy right now to type the math symbols, then that's fine. But if you're actually thinking about the problem in terms of the words yes and no, or like anything like that, in terms of proving and disproving, that's too abstract. I mean, make sure you have a goal that's actually a goal. Like, I need to make this bigger than that. But, okay. So what's one way that I could do that? actually one pretty straightforward way to do it. Yeah, you can just make them negatives, right? You use the same numbers that are negative. So, I mean, you gotta make A -1 this time, and B -2, just so the bigger one is still bigger. But, sure, right? So then these are just gonna be the opposites. Everything's the opposite of what it is over there. That's -1/3, and that's just gonna be -1/2 -1. So that's gonna work out the other way. It's going to be greater than or equal to. I mean, it is greater than, but again, as long as it's greater than or equal to, you're good. So, this is not sufficient. Yeah, negatives are fine. I mean, there's nothing here that's precluding the use of negative numbers. I mean, the only thing you can't do is you can't let one of them be 0. And so the product can't be 0. So, all that means is you can't use 0 for either number. And A plus B can't be 0. Well, that just means they can't be opposites of each other either. So yeah, nothing precluding negatives here. So there were a lot of people who picked D. And actually a lot of people who picked B too. Like a lot of people. But no, statement 2 is not sufficient. There it is. I think that's a big takeaway because I mean these are not crazy obscure cases or anything. I mean there were a total of 18 people here out of 30 something who actually. Sorry, there were a total of 12 people who thought that statement 2 was sufficient. Because that's adding up the people who picked D and the people who picked B. And actually, I think there were more than that originally because some people are shifting their answers now. So. A lot of people. I mean, big takeaway. Big takeaway. I mean, think about signs when you deal with inequalities. Because here, all you gotta do is just pick a negative, right? It's not anything crazy. Any questions about statement 2? Okay, now what's the deal with statement 1? Like, what do you think of when you look at this weird-looking statement? Like, what math concepts spring to mind when you see things that look like this? Does that make you think of anything? And that's what they are. They are absolute values. But I mean, like, what other math concepts are tied very closely into those? Yeah, signs, right, for sure. So like these should make you, I mean, because absolute values ultimately have everything to do with the sign of a number and very little to do with much else. So you should think about signs because there's absolute values. So, okay. When we know they can't be 0, so we only have to think about non-zero signs, which is nice because if they were allowed to be 0, we would have a lot more cases to deal with. But there's only 4 cases possible, right? You can just kind of think about it. You can just think about it exhaustively if you want. I mean, can you have positive? Can you have positive, negative? Can you have negative, positive? And can you have negative? And let's just talk about those. I mean, you can plug in numbers if you have to. If it's too abstract for you to think in terms of just signs, then don't think in terms of just signs. Go ahead and plug in. But yeah. I mean, if they're both positive, it's probably pretty clear that, hold on a second. So it's probably pretty clear that both positive will work, right? Because if you plug in 2 positives, then the absolute values are the same as the original numbers. Like if you imagine plugging in numbers like 5 and 4, then, still 5 and it's still 4. So positive work just fine. So, all right. What about the rest of these? So this will work. If they're both positive, it'll work. What about positive and negative? Will this work if one of them is negative? Nope. Because, I mean, if one of them is negative, notice that absolute A is still the same thing as A. But that's going to be less than that. So if one of them is negative, then that's going to make the left-hand side bigger. And that same thing's going to happen if it doesn't matter which one is negative, because the same thing will happen in both places. And if they're both negative, then the left side is definitely bigger, because if they're both negative, then the right-hand side is negative and the left-hand side is positive. So this is actually just a really, 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 really long-winded way of telling us that A and B are both positive. And again, the only reason if 0 were allowed, then we would definitely have to worry about those cases too. But we don't have to because it says we don't have to. That's important. So statement 1 is basically just telling us. Statement 1 just means that both A and B are positive. Okay. So I mean, you can start out with testing cases. You can start it out with the same sort of case that we had for statement 2. You can actually just import that first case. You can use 2 and 1. What's going to happen here if we try other cases? And I'll give the game away here just so we can get to other problems, but if you throw in a whole bunch of other positives, they're all going to do the same thing. You may see why that is. I mean, one thing you definitely don't have to try is numbers like 1 and 2, because these are symmetrical expressions. Like if this is A plus B, and this is 1 over A plus 1 over B, so switching A and B won't do anything. So, I mean, plugging in 1 and 2, if you do plug in 1 and 2, you'll discover that awfully fast anyway. I mean, you get the same result that you would from 2 and 1 if you plug in 1 and 2. But can anybody see the relationship? If these are positive numbers, can anybody see a relationship between this and these two? Relationship. Everybody sees where I'm going with that. Some typing. Like considering this expression versus these expressions. You can try to make that into A plus B over AB, but I don't know what that would do for you. The right-hand side has 1 plus 1 on top. I don't know where you're going with that, Kyle. I mean, if you can't just look at the numbers on the tops of the fractions. I mean, if you have, like, I mean, maybe you're implying more than you're writing here, but if you have something like this, I mean, if you had 1 1/2 versus something like 1/7 plus 1/8. I mean, 1/2 is bigger. So that's not necessarily. Aha! Yeah, look at what Dave's writing. I mean, if you think about it, these are positive numbers, right? I mean, let's just think about this. Forget 1/b for a second. I mean, just think about this. Just think about 1/a plus b versus 1/a. Just those two by themselves. I mean, which one of those is bigger? Notice that A, I mean, A is smaller than A plus B. So when you put 1 over those, it reverses that directionality, right? So like this is smaller, and this is actually already bigger. In other words, this is already bigger than that before you even add 1/b to it. And then 1/b is also bigger. So, yeah, if you, like each of these two fractions here is individually more than 1/a plus b already, because A is less than A plus B, so 1/a is more, and so forth. I mean, each of these by itself, each of these fractions alone is bigger than 1/a plus b already. So if you add those together, then of course, I mean, so in fact, these are going to be more than twice as big as that. And again, I mean, when you plug in numbers, you'll notice this pretty quickly, right? Like notice that 1/2 is already bigger than 1/3, and notice that 1 is already bigger than 1/3. You know, so when you add those together, and I mean, even if you try making A and B fractions, the same thing will still be true. Like if A is 1/4, then B is like 1/3. Then let's use 1/2 and 1/3. Then I gotta add those in my head. 1/2 plus 1/3 is 5/6. So 1/a plus b is 6. Okay. But notice 1/a is already 2, and 1/b is already 3. So again, each of these individually is bigger than that. So no question about it. So you're adding one smaller item versus 2 items that are each individually bigger than that one. So statement 1. What do you mean? Does it apply to both sides of? How can something only apply to one side of an inequality? And statement 1 just tells us that the 2 numbers are positive. And then this is what we're evaluating here. So no, you don't have to know that A is greater than B. I mean, in fact, I mean, you can actually tell when you look at this problem right away that you won't have to know something like this. Because if you look at these expressions, these are symmetrical expressions. Like if you switch A and B, then this is the same as it was, and this is also the same as it was. So just by looking at that, you can tell that A greater than B shouldn't matter at all. Because you need a certain amount of intuition about numbers and symmetry and stuff to realize that. But there's switching A and B in these expressions doesn't change anything, so it can't possibly matter which one is bigger. Like that can't make any difference because switching them doesn't change anything. Like if it mattered which one was bigger, then you would have to have some sort of asymmetric expression in here, like division or subtraction or something. So yeah, but if that doesn't jump into your head right away, you just test cases and you're good. But yeah, so this is going to be smaller versus bigger plus bigger. So this is always going to be less than. This is going to be sufficient. Pretty neat. So there you go. And this is A out here. Statement 1 is sufficient all by itself. Any questions about this? Yeah, one person typing. That would be not anything simple. You would probably just have to test random numbers there. I mean, I can't just tell you what the answer would be to that, but you would have to just try numbers and see. But if you, okay, statement 1 for statement 2. I'm not sure what you mean by that. What do you mean? What do you mean by use statement 1 for statement 2? Okay, where are you going? Remember how data efficiency works. Like you use the statements individually, and then you don't. Sounds like you're talking about putting the statements together, but we don't reach that point in this problem because statement 1 alone is good enough. So I mean I don't know exactly what you mean by use statement 1 for statement 2, but it sounds like it's some sort of reference to combining the two statements, which is not a point that you ever reach in this problem. So if that's what you're thinking about, then it doesn't happen. Because remember, you don't do that. You only combine statements when they're individually not sufficient. The answer to what is the difficulty level is you don't care. Okay, because you should not ever care about that. No possible benefit in thinking about it. Okay, let's do another problem. I mean, really, people ask this question in almost every single one of these, and I mean, there's zero benefit from thinking about it, and there's a lot of potential cost from thinking about it, because thinking about that will just take away brain power. I mean, my favorite analogy for this is imagine that you're getting shot at with someone's shooting at you with a gun for about 5 minutes, and you have to dodge the bullets and stay alive. If you're busy thinking about how difficult that last bullet was, you're going to die. So what's going to happen? You need to be spending all the brain power on dodging the bullets. So, I mean, the same thing is true here. I mean, any thoughts on extraneous crap like that is just going to make you worse. That stuff. I mean, same thing with, if you have the appropriate level of focus on the problems, because a lot of people are also talking about, oh, what if I got the last however many right or wrong or whatever. I mean, number one, you won't know. You're not going to know if you're getting these things right or wrong all the time. But number two, if you have any recollection of the last few problems, then that means that you're totally not paying enough attention to the problem in front of your face. I mean, that's the other thing. But you should have so much focus on the problem in front of you that that you should not even remember what the last few problems were, much less how you thought you did on them. Warcraft. I have no idea what that means, but okay. Unless you just need war, like warfare. But otherwise, I don't know what you mean by that. Okay. Okay, apparently there is an inside joke that I do not get because people are laughing at me. Okay, let's move on to the next problem. Let's do another one of these. Okay, how about this one. I mean, it's some kind of movie reference or something that I'm not gonna get those. Because I am totally not, nope. That's sort of pop culture stuff. Not very my world. Okay. There's a problem. Remember where you find multiple choice answers. Those are found here. Okay, we should probably pick a thing here pretty soon. Anything, there's not a lot of people without answers here, so I'm going to give you another minute or so on this thing. Pick an answer to this thing. Interestingly, there are about 25 answers so far, and about 2 of them are correct. So you definitely shouldn't feel bad about guessing. Definitely shouldn't feel bad about guessing. Okay. Let's take a look at your name. Yeah, I love my internet connection. No, I don't. Okay, this is a yes/no internet. This is a yes/no data efficiency problem, so you have the same kind of goals that you do in other yes/no data efficiency problems, right? So you have the yes case, which is that x to the fourth plus y to the fourth is greater than z to the fourth. And then you have the no case, which is that x to the fourth plus y to the fourth is less than or equal to z to the fourth. And those are the things that you want to make happen. And again, these are the goals, right? I mean, I strongly suspect that a lot of you guys who, especially if you have an answer like B or D, where you thought something like statement 2 was sufficient, I strongly suspect that you didn't really have these goals clarified in the first place. Because if you have these, at least with statement 2, you should be able to knock that out pretty quickly. I mean, statement 1 is a bit of an interesting animal here, but if you have these goals concretely specified, then statement 2 is not so bad. Okay, also, when it comes to questions like this, I mean, really, guys, when it comes to stuff like this, I mean, I know I've kind of delivered this life lesson in these workshops before, but just remember, it's the same secret that 90% of life is, which is do stuff and don't not do stuff. I mean, really, like, you should really try to avoid making yourself go through a whole decision tree of stuff before you even start doing a problem. Like, that's what you do not want to do. I mean, you should just do things. I mean, if you do, and like the other thing is you don't have any patience. That's not a universal life lesson so much. There are times in life when you do want to have patience, but in this test, no, you should not have any patience. So like basically if you feel like doing this algebraically, then you can try, but if it doesn't go anywhere, then you should just quit it. And the point is that you should not shove variables around the page for like 15 minutes before you quit. I mean, I've also said this before in these workshops, but like three of the biggest reasons why I have 2 perfect scores on this exam are I have no patience, I have no perseverance, and I don't really care about things that much. And like a lot of people really don't like to hear that, especially people who have this strong traditional work ethic. But it's true. This is how this exam works. I mean, like I pretty much, if something is not working, I kind of don't keep working at it because I'm just not that kind of person. And if you are, you really have to cultivate not being like that for this exam because it's how it works. And in terms of not caring about stuff, you have to be able to let go of the problem, guys. I mean, if you're not getting somewhere with it and you have to guess, then, life just kind of works that way sometimes. And you have to guess. And oh well, and you let it go. So you can't care that much about any one particular problem. So, but okay. So can you simplify the original expression? You tell me, can you? Is there a way to simplify a sum of squares or even power? There's not really one that I know of. I mean, unless you got into things like imaginary numbers, which is probably not going to be your friend here. So differences of squares you can simplify. I mean, simplify is the wrong word anyway. Because like if you make, a squared minus b squared into a minus b times a plus b, you're not really simplifying anything. You're just transforming it in a different form. But like it should be clear that there's no. Oh, okay, I mean, I'm being nitpicky with words here, but here are 2 differences. Like if you have x plus x and you change that into 2x, that's simplifying. If you have something like a squared minus b squared and you change that into a minus b times a plus b, this is not simplifying. Because neither of these directions is simpler than the other one. And I mean, it's important to realize this because, like, simplifying, that is, like, smiley face, you're going to see what I'm talking about here when I say this. Because, like, a lot of people are really throwing around the word simplify today as though in a way that's totally wrong, and so it's worth this time to talk about this. Because, like, simplifying that's actually simplifying, like this, you should always do, and there's no reason to ever not do it. So, like, if you have an x plus x somewhere in your expression, you should always make that 2x immediately whenever you see it. If you, anything like that. If you have 10 over 2, you should make that 5. You get the point. So, but here, these are not, there's no simplifying of this, because that would imply that one of these is better than the other one. And that each of these is useful for different reasons, right? So you might want to convert this into that, and you might want to convert this back into this. So I'm kind of being nitpicky with words here, but I'm not really being nitpicky with words, because the way that you think about things that are actually simplifying is very different than the way that you think about stuff like this. Like stuff like this you do only if you have a reason to do it, whereas things like this you just do. You just do them and then you turn your brain on. It's a big difference. So, I mean, in that respect, it should be pretty obvious that there's not really any way to simplify this or this. I mean, I can't even think of anything algebraically to do with them at all, but there's definitely no way to simplify them. So that much should be clear. So, well, so if you don't know whether you can do things like that, because like some people in the sort of heat of the moment or whatever will forget whether certain types of algebraic rules work or not. So like some people, like the question is, can I take this root? I mean, this is squares, but same difference, right? Like if you forget whether you can take this and make this into x plus y, I mean, some people forget about that, right? So then just try numbers. And let's just try, like, x is 2 and y is 3. Then this is going to be the square root of 4 plus 9. And this is going to be 2 plus 3 is 5. That just doesn't work. I mean, you can totally do this on the fly, like during the time that you have for the problem. I mean, this is not something that you don't have time to do. So if it doesn't work for square roots, it's definitely not going to work for fourth roots either, because same deal, right? So okay. But yeah, do stuff, don't not do stuff. So like, the point here is like if you try algebra, it doesn't go anywhere. You need to quit as soon as you are not 100.00000% sure that you know where you're going. I mean, this needs to be like driving your car somewhere where you're sort of late. Like the minute that you are not absolutely sure you are not driving in the right direction, you will pull over. Like you don't just keep driving until you are hopelessly lost. This is the same thing. Like you should not keep shoving X's and Y's around and hoping that cool things happen, because they won't. Okay, but long story short, if you try algebra in this problem, it doesn't really work. So it doesn't try it. It's not going to go anywhere. So if you can experiment with it, but the point is this moment should come pretty fast. This moment of like, oh crap, I don't know where I'm going with it. So anything like that, it's going to be randomized. They're very good at randomizing stuff. So if you're legitimately down to C and D, it's probably about a 50-50 shot. Okay, let's take a look. So these are the two goals. If you can make these both happen, that is not sufficient. Sure. Okay. Typo. Let's fix that. Let's do statement 2, because again, statement 2 is a little bit more friendly looking. There we go. Remember, when you do these things, your first case can be random. I mean, you don't need to use your brain to start strategizing until your first case is there, because then your goal becomes to find whatever didn't happen in the first case, right? So like, what someone give me a set of numbers, x plus y greater than z. Give me some numbers. Jaya is going to give us some numbers. No. What do I have? 2, 3, 2 plus 3 is not greater than 5. We can't use that. No, we have to make the condition true. We're for statement 2. Statement 2 we're going to use first. Sorry if that was unclear. Although those don't. 2, 3, and 5 don't work for either statement, so be careful with that. Guys, 2, 3, and 7, that doesn't work for either statement either. And remember, you have to make these things true. So, but yeah, let's use 2, 1, and 2. Let's do that. First, someone said 2, 1, 2. Okay, and then what we need to do with this is we need to actually find x squared plus x to the 4th and y to the 4th, and then find z to the 4th. And then we need to compare those. Okay, so here x to the 4th plus y to the 4th is, and then yeah, Anthony, I like how you did that, so we'll do that. We'll do that. 2 and 2 is totally random choice of numbers. It's completely random as long as it satisfies this. I mean, remember, your first choice of numbers can and should be completely random without a lot of thought, because then it'll make one of these happen, and then once one of these happens, then you can start strategizing all you want by making the other one happen. So, I mean, if that makes sense, actually, because. Yeah, okay, first case random. So actually, I mean, this is going to be, well, it's 16 plus 1, which is more than 16. So that's more than, look at that. So now the goal in life that we have is to make the left-hand side, to make x to the fourth plus y to the fourth less than or equal to z to the fourth. Okay, I mean, while still keeping this condition true. So I like the way that Anthony did this. Because, yeah, I mean, the thing is, like, this shows one way to strategize this pretty well. I mean, if you make these 2 and maybe 3, and then this is like a negative number, we can even just keep that as 1 for now, because then this is still 16 plus 1. But then, like, z to the fourth is something really big. So that's going to definitely be less than or equal to. Sure it is. That's kind of neat. So this is now sufficient. It's not the only way to do it, but this is a very accessible, straightforward way to do it. So, sure, this is not sufficient. Is it the only way? Not in the least. I mean, there's plenty of other ways to do it, but it's convenient. I like that. Okay. Now for statement 1. So as far as how to make the table for this stuff, I mean, what you should do is just think about what you have to do. So for statement 1, you're going to have to pick an x and a y and a z. That's the first thing you're going to have to do, of course. Alright, I think I'm back. My internet is just lovely. Okay. This is statement 1. You want to check this to make sure that it's actually true. It's a good idea to put a check in your table. I mean, honestly, it'll be faster than if you try to do it in your head. I swear it will. Especially if you're dealing with, I mean, negatives and stuff like that. I mean, here, negatives won't help you. These are all even powers anyway, but just put it in the table, guys. I mean, don't make yourself remember stuff. Making yourself remember things is always bad. Okay. And then once you check that, there you go. There's a nice little system. You can make columns if you want to. Okay. How about that? So, what's one very easy way to make this true? Remember, your first case can be random again. Yeah, you could just make them like 1 and 1 and 1, or even Z could be 0 or something, but something like that, right? One of these easy cases. So 1, 1, maybe even 0. Okay, 1 plus 1. 1 plus 1 is definitely greater than 0. So this is still 1 plus 1, and this is still 0. All right, that's greater. Same goal in life. Goal in life is to get greater. Now is to get less than or equal to. That's what we want. How are we going to go about doing that? Two, 5, and 7. Okay. If we try 2, 5, and 7, then this isn't going to work. Yeah, if we try 2, 5, and 6, okay, let's try that. This is exactly why we want this middle column in our table. If we try this, it's going to fail it, right? 2 plus 25 is not greater than 36. So that's not a case. We can't use that. So this is just gone. Yeah, if we try negatives, it's not going to do anything different because when you square, I suppose you mean even exponents when you wrote that. Because we have second and fourth powers here, yeah, this is just going to become positive. So, I mean, okay, when you have 2, 5, and 5, if you remember what the goal is. The goal is to try to make this left-hand side less than that side. So, I mean, if you have a 5 here and one of these is also 5, that's definitely not going to happen because you know something else to the fourth plus 5 to the fourth is definitely going to be bigger than 5 to the fourth. So there's no point in trying that. What about fractions? Oh, hey, cool. Also, Dave, your example works too, which was a different sec. Let's try fractions. I mean, what makes you, Andy? What makes you think about fractions? Did you just come to you in a dream? What made you think about that? I mean, so no integer constraints kind of sounds like you're thinking of fractions at random. Although there's a good reason to think about them here. Yeah, that's a good reason to think about it, right? Because fractions have the opposite behavior. Yeah, right. Fractions get smaller with bigger powers. So they might make it easier to do this. I mean, they might make this happen. So sure. I mean, let's see what we can do with that. And then if we're trying to make this happen, then like we should, like x squared plus y squared still has to be greater than z squared. But we should try to make it as x squared plus y squared shouldn't be that much greater than z squared because we wouldn't want it to be that much greater. So like, because the idea is that we want this to be bigger than that, but then we want these to get smaller, right? So like, the goal here should be, I mean, we want this to be barely bigger. And so then there's in the hope that this will become the other way around when we do it with fractions. So again, we think about that, right? Like here are some like if you square 1/2, you get 1/4. If you square 1/3, you get 1/9. If you square 1/4, you get 1/16. Aha. I mean, if you think about that? If you try 1/4 and 1/4 here, then x squared is 1/16 and y squared is 1/16. That's 1/8. What can we pick for z? And for z, not for z squared. So, third's a good choice there. Absolutely, right? Because then that'd be 1/9. Because then 1/8 versus 1/9. 1/8 is still a period of 9. That works. That works. It's very close, and that's what we wanted to do. So then x to the 4th plus y to the 4th. Wow, that's 1/16 squared. So 1/. 1 over 16 squared plus 1 over 16 squared. And then z to the fourth is 1 over 9 squared. So that's 1 over 81. Well, 16 squared is pretty big, right? This is it's about 200 and something. Because 15 squared is 225. So this is 16, 256. So this is 1 over 256. That's actually a lot smaller. And that shows us that we've actually got some room to work with here. Because this is 1 over 128, and this is going to be a lot less than that. So 1 over 81 is z to the fourth. Their value of z. We're just plugging it in. And remember these are the values. Like this is not a value of z. This is just a statement 1 that we're checking. So this is what we want. So this proves the statement's not sufficient. How about that? I mean, do you have to do with fractions? No, actually you don't. I mean, because if you had to come up with values like this, I mean, they probably wouldn't write a problem where you had to come up with some special thing like that. I mean, you could also just do what Dave noted up there in the chat box. But again, like if you notice, right, like again, you can notice that we want that to be just barely bigger, so that maybe this will get smaller. So if you think about this in terms of integers, I mean, if like 7 squared is 49, and 49 is like just barely less than 50. So if you just use these numbers like these, then you got 25 plus 25 is greater than 49. Yeah, that works. Just barely, yeah, you're right. That's what we want. We want it to be really close. And then x to the fourth plus y to the fourth, that's 25 times 25 plus 25 times 25, then that's 49 times 49. So notice this is, you can, like 25x plus 25x is 50x. Similarly, this is going to be 50 times 25. And I mean, this is almost 50 times 50. So this is going to be like this is almost twice as big as that. So this is going to be way bigger. Like this is not even sort of close. So again, we win. This is less than or equal to. You can make that work. It's kind of cool. So you don't have to come up with fractions. The point is you just have to kind of keep throwing numbers at it and see what happens. At the very worst, what you can probably do here is you can probably look at it, and because a couple of you guys looked at it and thought, oh, hey, maybe I could just like square or root the top, and it'll give me statement 1. And when you think that, you should look at this problem, and you should probably think things like, wow, I bet it doesn't work like that. And so, that should predispose you against thinking these things are sufficient. I mean, you're still not going to be able to avoid having to plug in the numbers, but if you have to guess something, you should definitely guess the non-obvious looking situations here. So that's the thing. It seems like there are no constraints. I mean, I don't know if I'd say that so much, because like if you look at the not really, because like the constraints in this problem were not like real constraints. I mean, like AB not equal to 0 just means you can't make it 0, but that's not a serious restriction on the numbers. And then like this just means that A can't be the opposite of B. But I mean, like the only thing we're trying to do with these is just to make sure that we're not dividing by 0. So, but apart from not dividing by 0, like these numbers are pretty much unrestricted because these numbers could be anything that makes you not divide by 0, and that is still sufficient. So, I wouldn't go there. I mean, like, if there was any sort of superficial guessing methods like that, these guys would be very good at making it not work. And then that's one thing that they do very well, the creators of this test, is they make sure that superficial guessing methods don't work. I mean, really, like if you come up with anything like, if I see this or that superficial feature of the problem, then I'm going to guess this, you're just guessing. Like there's no way that will get through their filters. Because they run statistical analyses on these things and they make sure that nothing like that really sees the light of day. So, yeah. Internet connection. Yeah, the last thing I was saying while this screen was up here was it was this question about that Anthony was asking here about this. This is not really a thing because like this problem basically has no constraints either, and this statement was sufficient. Yeah. I mean, like, 'cause these are not really constraints. I mean, these are just things that ensure that the denominators are not 0, but that's all they are. So effectively not really constraints because right. So effectively this is a no constraints problem where that's still sufficient. And what I was saying, I don't know if this got through before the internet went out again, but if there was anything like that was that superficial that worked as a guessing method, they would have gotten rid of it 10, 15 years ago. They're pretty good about not making easily guessable problems. So, and that's one thing they do very well. As far as this question, I mean, if you, this question right here, I mean, remember what the goals are, right? Like we needed this goal. I mean, we got the greater than. So we were talking specifically about the situation where this was the goal that we wanted. So that where we're talking about this, that was to achieve that goal. Right. Smiley face if you followed that, Jaya. Okay, so if they didn't want that goal, then all you got to do is think about the fact. I mean, think about what other numbers would do, right? Like if x squared plus y squared was way bigger than z squared, then this would stay bigger than that. I mean, it just would. Like if these numbers were like 1,000 and 100 and like 5, then left-hand side would be bigger. So if you go through a couple examples, you'll eventually realize it pretty quickly. And then the only way that you would have any shot at making this smaller than that would be if this wasn't that much bigger than this in the first place. So you don't put the two statements together because you don't. I mean, you do. Okay, yeah, you do. So if you put them together, then so we have these two statements right here. These cases. These both work for statement 2 as well. So because we generated these for statement 1, so for the two statements together, we just need to check statement 2. So if we do that, well, 1/4 plus 1/4 is greater than 1/3. So that works. So that works for both statements. And then 5 plus 5 is also greater than 7. So as it turns out, these cases both work for both statements. And yeah. So if this proves that it's E, because even if you combine the statements, you can still use the same two cases for this. So if they were integers, I mean, we got a case on the screen where they're integers that shows that it's not sufficient. So I'm not sure why you're asking that. I do. This question right here. I mean, did you notice this whole workup down here? And these are all integers. So not sufficient. Because those are integers. We've actually proved it with integers. Still E elephant. Because we used 5, 5, and 7, and they worked both ways. Okay. Other quick questions about this one. But yeah, this is a great problem in terms of do stuff, don't not do stuff. Just throw things at it and try not to overthink it in advance, because good problem for that. You just really don't know. You don't know they're going to throw it at you. You don't really know how this stuff is going to affect it. But you can just throw stuff at it, see what it does. It's pretty neat. Cool. Any questions that are super quick? Otherwise, we'll go ahead and shut down the show. I mean, we definitely have more of these inequality problems to go, because I think we only did 2 problems today. So, yeah, E like elephant. So let's kill it for now. We're going to come back to more inequalities probably next time. And very neat. Cool. And I'm going to kill the recording here. It is, as we've said a couple times, it is E like elephant. All right, good afternoon, good evening, good night, good luck.